Okay, so this is a last lecture on nonlinear programming. We will talk about nonlinear programming algorithm, and then after this lecture, we will start talking about integer programming and mixed integer programming. As you recall, right, when we talk about like linear programming, we first talk about geometric properties, then we talk about optimality conditions, then you can derive an algorithm based on optimality condition, right? As you recall from the previous lecture, we derived something called KKT conditions under some constraint qualification. For convex problems, KKT conditions are both necessary and sufficient conditions for convex optimization problems, right? So therefore, we can try to derive an algorithm based on this optimality condition, right? And since the KKT condition involve both the primal and dual, not only we can try to get a primal feasible solution, we can also use that condition to estimate how far the solution is from the global optimum, right? Recall that in linear programming, whenever you have a primal feasible solution and you have a dual feasible solution, right? The dual feasible solution can give you an estimate how far the primal solution is from the theoretical global optimum. So that's something similar we can do with a so-called interior point algorithm in nonlinear programming. Okay, so the outline of this lecture is as follows. We will first talk about a very simple algorithm called equality constraint, Newton's method, meaning that we only have linear equality constraint. The objective can be nonlinear, but the constraints are all linear. And after that, we will talk about two types of interior point method. The first one is called barrier method. Then the second one is so-called primal dual interior point method. Okay, so you don't need to be scared by this. This is just an outline. Okay, so now let's start from this simple problem. Remember, in convex optimization, if we have equality constraints, the equalities have to be linear. So let's think about how do we solve this type of problem. So if you have a nonlinear objective function, but the objective function is convex, minimizing f of x subject to ax equals to b, right? So there are two options we can use to solve this problem. The first option is to do a very simple linear algebra trick and convert this problem to a unconstrained optimization problem. So how do we do that? So if you know x satisfy ax equals to b, right? So remember in one of the lecture, actually the previous lecture, we talked about when does ax equals to b have a solution, right? It has a solution when b is in the column space of a, right? So if this problem is feasible, right? If the problem is infeasible, it's not of interest, right? Now, then you can write the solution x as x0, which is an arbitrary solution to ax equals to b, right? And f, which spans the null space of a. Right? So that means if you take any columns in this matrix f, a times the column equals to 0. So if you think about f as, let's say, a vector f1, f2, all the way to, let's call it maybe fl, right? So all these satisfy af equals to 0, right? That means f is in the null space. Therefore, if x0 satisfy ax equals to b, for any linear combination of these vectors in the null space plus x0 also satisfy ax equals to b, right? So therefore, any solution to ax equals to b can be represented in this generic form, right? If f contains all the, let's say, basis vector in the null space of a, right? So now you can solve this problem in terms of y as an unconstrained optimization problem by removing this constraint and then replace x with fy plus x0. right? So this automatically satisfies the linear equality constraints, right? So now you can optimize in terms of y instead of in terms of x, right? And now y is unconstrained. You can use any of the unconstrained optimization algorithm to solve this problem. Okay. Now, there is also another method to solve this problem. What if you don't want to express x in terms of null space and so forth? We can also borrow the idea from Newton's method, right? Recall, the idea of Newton's method is doing a second order Taylor series expansion of the function f of x, and then you optimize over that quadratic approximation. Right? If you do up to second order, that's a quadratic function, then you can optimize that quadratic function. Now, similarly, you can also do a quadratic approximation when it's linearly constrained, right? So here, let's think about if you are at a particular point x0, where at x0 is a feasible solution to the linear equation, right? Then at each iteration, you can solve a quadratic approximation of the original problem, right? So suppose you want to find a vector v such that you take a step v to minimize this problem, right? So if you consider a perturbation of x plus v, then you can do a second order Taylor series expansion. So this is a second order Taylor series expansion, right? Now the constraint is linear, right? So then you can just keep the constraint as it is, right? You still need to satisfy these linear equations after you add this perturbation v, right? So now what you have is, here's an objective function, right? The objective function is a quadratic function of v, right? You want to perturb x by v, satisfy some constraint. This is nothing but a times v equals to 0, right? Because if you assume your original x is a feasible solution, then v has to satisfy a times v equals to 0, right? Okay, so now what problem do you have? You essentially have a quadratic objective function subject to linear constraint, right? If you recall the last slide of the previous lecture, we actually talk about the KKT condition of this problem, right? A convex quadratic objective function subject to linear constraint. Then if you write down the KKT condition of this problem, it is nothing but these linear systems here, right? You have the Hessian of the original problem, and then you have A and A transpose in the diagonal. Okay, so this is a primal variable, right? And this is the W is the dual variable you have. And in total, you have the same number of equations as the number of constraints. You can just solve a linear system to get a Newton step for this problem. Okay, so again, now the Newton direction V is, again, solving a linear system in Hessian, right? It's not the original Hessian, but in a sort of expanded Hessian by considering your linear equality constraints, right? And similarly, you can do things like backtracking line search using the Newton's direction, right? As we talk about in the unconstrained optimization lecture. Okay. Any questions regarding this? Yes?
Yeah, so what is the NT referring to, and is W just the dual variable in this case?
Oh, yeah, exactly. The W is a dual variable in this case. Delta N, you can think about delta NT as the optimal step, or the optimal Newton step, right? So here you are writing this problem generically in terms of V, right? The V that minimizes this problem is written as delta XNT. That's a Newton step that minimizes this quadratic approximation.
Okay, so
right.
delta XNT is essentially?
Yeah, essentially the optimal V.
It's the best V.
Yeah, exactly, yeah. Okay, any other questions? All right. So, So then you could implement Newton's method in the same way as you implement the Newton's method for unconstrained optimization problem. Since we've talked about this before, I won't go to the details. The idea is you need some stopping criteria. In the Newton step, we use this lambda x as a stopping criteria. If you don't recall that, you could go back to the Newton's step lecture. And then similarly, we need to do some sort of line search to make sure not only we have a good gradient, but then you want to have a sufficient decrease in your objective function. Okay. Yeah. So in terms of algorithm, as you can see, the equality constraint nonlinear programs is very similar to unconstrained problems. Right? There is nothing inherently different. You could even reformulate it as an unconstrained optimization problem. Okay. But the challenge here in solving convex nonlinear problems lies in the inequality constraints, right? Because we don't really know how to get rid of the inequality constraints easily, right? So here, let's start talking about this particular problem. We assume f of x is a convex problem. Then all the inequality constraints are described as hi of x, and all the h are convex functions. And we assume they are twice differentiable. Right? Because sometimes you want to get the second order derivative. Let's just assume they are twice differentiable. Okay, and then each of these has a domain Rn. Now you also have some equality constraints. Okay, that's a problem we are targeting here. Okay, so in the next few slides, we will ignore the equality constraints for now, right? Because we already did some math and show you that if you have equality constraints ax equals to b, it is easy, right? You can just convert it into an unconstrained optimization problem, right? So therefore, to simplify the notation, we will assume there are no linear equality constraint. But you know that there are some tricks you could easily handle the linear equality constraints, right? So now let's forget about these equality constraints for now. The only constraints we have are those hi of x less than or equal to 0. Okay. Now, the first algorithm is called the barrier algorithm. The idea is to use some function called a log barrier function to approximate these constraints. Okay, so let's gradually develop this method here. Right? So first I'll note that the problem we are considering is minimizing f of x subject to hi of x less than or equal to 0. Right? We ignore the equality constraints for now. And then the idea is, instead of putting those hi of x less than or equal to 0 in the constraints, we put all the hi of x less than or equal to 0 in the objective function. Okay. So what is this notation here, denoted by I minus? So this function is so-called indicator function. Okay, how does that work, right? So the indicator function is saying if the argument of this function is less than or equal to 0, right? Note that the argument here is hi of x, right? So hi of x less than or equal to 0 means this problem is feasible, right? So if u is less than or equal to 0, the function value equals to 0, right? So if hi of x is less than or equal to 0, the x is feasible. Therefore, there is no penalty to the objective function. On the other hand, if you have u greater than 0, right? So here again, the argument is hi of x. If hi of x is strictly greater than 0, that means this x is infeasible, right? So if the x is infeasible, this indicator function will induce an infinite penalty to the objective, right? Okay, so Therefore, if you have the sum of the indicator function applied to HL of x, if the x violates one of these constraints, right, there are in total m constraints. If x violates any of these constraints, the objective will go to plus infinity, right? So in order for x to be feasible, or in order to have a non-trivial objective function that is not plus infinity, we must have HL x less than or equal to 0, right? Okay, that's sort of a reformulation of the original problem using the indicator function, right? Since we are minimizing, you must be choosing some x that is not plus infinity, right? It's not interesting to get a objective of plus infinity. Okay. So is this reformulation clear? Okay. Yeah. So now the thing is, there is no free lunch, right? You replace these very hard constraints with an indicator function, right? So how does the indicator function look like, right? So let's maybe plot it on the u-axis. So this is u, right? When u is, let's say, less than or equal to 0, the indicator function is 0, right? So, and then as soon as the u is greater than 0, right? So let's say this is the origin. As long as the u is greater than 0, then this quickly jump to plus infinity, right? I cannot draw plus infinity. Let's assume it's arbitrarily higher up here. This is plus infinity, right? I mean, this function has very bad properties, right? It is discontinuous at this point here, right? U equals to 0. And of course, when it's discontinuous, it's non-differentiable. Therefore, you cannot directly solve this optimization problem, right? It's super difficult to solve this problem. Okay. Now, the log barrier algorithm is to say, instead of having an indicator function, we will introduce something called a log barrier function to approximate the indicator function. Okay, and the log barrier function looks like this. It's minus 1 over t, the summation of all the constraints, log minus HL x, right? So let's think about how this function will look like, right? How does a log function look like? It looks like something, so this is 1, right? So this is, let's say, log of x, right? As you can see, the domain of log of x must be greater than 0, right? But now if you have, minus HL x to be greater than 0, that means HL x must be less than 0, right? So this log function kind of keeps the h of x feasible, right? Keeps the HL x to be less than 0 using this log function, okay? Now, what does this 1 over t do here, right? So then let me show you how this function looks like. Okay, so in this figure, it shows the function minus 1 over t times log minus u, right? So since you have minus u here, then the u must be less than 0, right? Since the domain of log of x is greater than 0. And now these 3 different curves shows you these function for different values of t. Actually, it shows you for the value of t equals to 0.5, 1, and 2, right? So where does the approximation comes into play, right? The approximation is to say you want to keep this curve to be close to 0, right? Such that whenever it is feasible, you do not introduce any penalty. Okay. Now, as you can see on this curve, as t increases, this function will approach the indicator function you want to approximate. Right? So you can think about this as t goes to infinity, this log function will be very close to this particular indicator function here, right? Because you want to set this part, this whole thing to 0, right? It only happens when t is a very big number. Then you can set these values close to 0. Okay, that's a trick here.
In this case, it doesn't really matter what type of logarithm you use, right?
Right, because it will only be off by some sort of constant. Right? You can always increase the t.
Gotcha.
Right, yeah. Usually people use natural log. Yeah. Okay, so now you can see the log barrier problem will give you an approximation of the original problem. But then in the next few slides, we will kind of estimate or analyze the property of this log barrier problem. Right? So before we analyze the property of the log barrier problem, I just want to give you this particular slide, right? Because whenever you solve the optimization problem, you are interested in the gradient, the Hessian, and so forth. Right? You can treat this slide as sort of like a cheat sheet here. Okay. Again, this phi is the minus log minus HILX, right? There is a summation here, but now I'm removing the t because 1 over t is a constant. It doesn't matter that much, okay? So what is the gradient of this log function? In order to calculate the gradient, you can use the chain rule, right? You have a log of minus HILX here, right? So when you take derivatives, like 1 over log of x derivative is 1 over x, right? And now using the chain rule, you got 1 over HILX times the gradient of HILX. Now, what about the Hessian? You could do the math yourself, applying chain rule or the quotient rule and stuff like that. The Hessian looks something like this. Okay, so the Hessian involves 1 over HI of x squared times the gradient times gradient transpose. Then here it has the Hessian of each of the constraint. Okay. So one interesting property, actually a necessary property for the log barrier function is, after I introduce the log barrier function into the objective, let's suppose if the original problem is convex, right? All the HILX is convex, is this function convex, right? So if this function becomes non-convex, that's a big problem, right? If my original problem is a convex problem, now I introduce a log barrier function to approximate the original problem. If the problem now becomes convex, then I'm kind of screwed, right? I turn the convex problem into a non-convex problem. But then you can do the math and quickly show that the Hessian of this function phi is positive semi-definite. Then we are good, right? The log barrier function remains to be convex. How do you see that? Here, this is like a vector times its transpose, right? This is, of course, is a PSD function, right? If you do that, it is like a square. Now, what about the second part, right? If the original problem is convex, the Hessian of each of these HLX is positive semi-definite, right? And now, I know the log barrier function will keep the x feasible, right? In order for this log to hold, this minus HILX must be greater than 0, right? So you have a minus times 1 over HILX here, right? For any x that is feasible, this part is positive, right? So we have some positive number times the Hessian of the original problem. Therefore, the Hessian of this function phi remains to be PSD. Okay, That's an important property of the log barrier function. Now, how does the algorithm work, right? So the way it works is at each iteration, you can pick a value of t greater than 0 and solve this convex optimization problem. We are, remember originally I have f of x plus 1 over t phi times 1 over t times phi x, right? This objective is equal to t times f of x plus phi x. You just multiply t to this problem, right? If you multiply a strictly greater than 0 number, it doesn't change the optimal solution. So now I know that phi x is a convex function, f of x is a convex function subject to some linear equations, right? I can use Newton's method to solve this problem. Right? We talk about how to solve convex optimization problems with equality constraints. Right? Okay. Now, the hope is that as t goes to infinity, we will have x converges to the optimal x, right? Recall that as t goes to infinity, the log barrier function will approximate the indicator function, right? Yeah. In practice, in this algorithm implementation, you will gradually increase t. Right? We won't start from t goes to infinity, right? That will cause a lot of numerical issues. So in practice, what people find out is we start with a small t, solve the problem, then we gradually increase t and solve that problem, right? Okay. Now, the question here is, we know as t goes to infinity, this barrier problem is equivalent to the original problem. Right? But in reality, you never set t equals to infinity. Right? You must have a finite number of t. The nice thing with this problem is you can always get a primal feasible solution. Right? Since you have this log barrier term here, right? In order for this log term to be defined, the x must be feasible, right? So you're always keeping the problem feasible by having this log barrier term, okay? But the issue is you always have a primal feasible solution, but how do you know the primal feasible solution is good enough, right? So the only thing you know is as t goes to infinity, it will converge to the global optimal solution of that problem. Of course, in practice, you cannot let t goes to infinity. T must be a finite value, right? Now the motivation is that how do we get an estimate of optimality gap with just a primal feasible solution, right? Okay, so that's what we are going to show you in the next few slides, right? So again, the idea is in order to get a lower bound or the Lagrangian bound for this problem, we need to use something like KKT condition or the Lagrangian dual, right? Just like what we did in linear program. In linear program, you could run simplex algorithm, it will terminate in a finite number of steps, right? But then if you don't want to run, let's say, simplex algorithm to termination, you can have a dual solution, right? If you have a dual solution and the primal bound is close enough to the dual bound, you can terminate, right? But here, the thing is that even in theory, right, we cannot terminate in a finite number of steps if we just focus on the primal of the log barrier problem, right? Because if t does not go to infinity, we cannot show the problem is equivalent to the original problem. It still has some sort of approximation. right? But now how do we actually determine when should we terminate when we have this log barrier approximation, okay? Or in other words, how to estimate the duality gap of the original problem. Okay, so this proof is a little bit complicated. Let me write it down slowly. Okay. Now, let's write down the log barrier problem in closed form, right? So we are solving this problem. X t times f of x should be minus log okay, and then subject to ax equals to b, right? So at each iteration of this problem, we can use the Newton's method to solve this problem, right? The Newton's method does not need any dual solution, right? And they can also terminate, right? So let's suppose, let's say using the Newton's method, we got an optimal solution. Let's call it x star t. Okay. Again, the Newton's method doesn't even need to know what the dual solution is, right? What the optimal dual solution is. But since this is a convex problem, right? Let's suppose this problem satisfies constraint qualification, right? So if x star t minimize this problem, it should also satisfy the KKT condition for some dual variables, right? So let's write down the KKT condition for this problem. Oh yeah, there should be a summation. Okay, so this is the stationarity condition. Then we have primal feasibility. And then we have, in order for the log function to hold, we must have hi of x star t to be strictly less than 0, right? So this dual is chosen such that it satisfies the KKT condition, right? So whenever x star is a primal optimal solution, there must exist some dual variables that together with x star, they satisfy the KKT conditions. You don't have to take notes. I will post this online, right? So this is a, let's say, optimal dual variable. Okay. Now, note that the goal here is we want a lower bound of the original problem. Okay. I mean, the fact that you solve the log barrier problem doesn't directly give you a lower bound of the original problem, right? Because you change the problem itself, right? It's not like you directly solve the original problem, then you get a dual feasible solution, then you get a lower bound. But now you didn't even try to solve the original problem, right? So let's write down the original problem here. Right, so there are m constraints. I will ignore all the m constraints, just write it as this. Okay, so we want to get a lower bound of the original problem. Now the idea is, if we can get the Lagrangian function at a particular dual variable, then we can get then we can get a lower bound of the original problem. Right? So let's remember the Lagrangian function g u v is nothing but minimizing x f of x plus the summation of I from 1 to m. Let's call it ui hix plus, let's say, v transpose b minus ax. Right? So this is a Lagrangian function of the original problem. Right? In order to get a lower bound, what we can do is that we show for a particular Lagrangian multiplier, we got some x that minimize this problem. Right? Okay. So now the way this proof works is it will show for a particular Lagrangian multiplier, you can show that this x star minimizes this problem. Right? Okay, so if you can show that this x star of the log barrier problem is a minimizer of some Lagrangian, then you got a lower bound. Right? Then now the idea is which u and v does x star minimize. Right? So here the claim in this proof is the following: if you set u star I t equals minus 1 over t times hi x star t and v star t equals to the dual variable over t, then x star t minimizes this particular function. Okay, so again, now since you already solved the log barrier problem, you got the optimal solution. You can treat this problem, this x star t, as a number. Right? You have already solved this problem, so therefore this x star t is a number. Now what I'm claiming is, if you set the dual variable to be this particular value, right, then you can construct a dual feasible solution using x star t and primal dual feasible solution. Okay, so it is a little bit lengthy. I will directly show you the notes. Okay. So here you set u star and v star to that particular value I just constructed. And then you can show that the x star minimize this particular problem because this is nothing but the KKT condition of the barrier problem. Right? You can compare this notation with the other one. How do I? Okay. Yeah, maybe I will just skip the math here because this is not so interesting. You could just check the math and believe me that if you set u star and v star to be that particular value, then you write down the optimality condition for this problem. It is equivalent to the KKT condition of the barrier problem. So therefore, X star minimize this particular function.
So in this case, how do we obtain like kind of our optimal dual like W?
Yeah, that's a very good question. Okay, so here I'm just represent. Suppose there exists a dual that optimize the barrier problem, right? Here I'm only showing you a property, right? And using this property, we will try to get the dual bound for the original problem.
Okay.
Right. So here just assume there exists a dual.
Got it.
Yeah, that's a very good question. Okay, so now if you, let's say without going to the details of math, it's more like a high level idea, right? If you pick this particular dual variable and then you find out X star indeed minimizes this function, then this GU star, V star is a lower bound of the original problem, right? Okay, so then let's check what is GU star V star, right? So if you write it out, and then if you by what I told you is X star minimizes this function, therefore you can plug in X star T here, right? Since it minimizes this dual function. Then what we have here is Fx star times U star Hi X star, and then this Lagrangian for the equality constraint. Okay. And since X star is a feasible solution to the log barrier problem, right? So Ax star minus B equals to 0, right? That's so we can eliminate this term. And the U star we picked is this particular term here by construction, right? So this will be reduced to m over t because the Hi X star and the denominator will cancel out, and they are in total m of these terms, right? So at the end, what you get is this lower bound is equal to Fx star minus m over t. Okay, so now you get rid of the W term because by construction, it doesn't appear in this summation here. Okay. So therefore, Fx star is a primal feasible solution. The log barrier always gives you a primal feasible solution. And this Lagrangian function is the Lagrangian function of the original problem, therefore it is a lower bound. Okay. Now you can think about the optimality gap as m over t here. Right. Okay, so this is a very simple result, but the proof is not so trivial, right? The nice thing about this result is you don't even need to calculate the dual variable in order to get a bound for the log barrier problem, right? We didn't even explicitly calculate the dual variable. It's, by derivation, we know that whenever you solve the primal problem for the log barrier problem, it is bounded to the optimal objective by m over t. M is a number of linear equality constraints, and t is this 1 over t ratio you choose, right? As t becomes larger, the gap becomes smaller, right? And this is very consistent with our intuition because as t goes bigger and bigger, it will converge to the indicator function, right? So that it shows you that the rate of convergence as you increase the number t here. Okay. Now, there is another way to interpret the log barrier problem. You can think about the log barrier problem as applying to this perturbed KKT condition. Right? You are solving this perturbed KKT condition where the complementarity condition does not hold exactly. You have the dual variable times Hi equals to minus 1 over t, right? So the complementarity condition is this is strictly 0, but if you take the primal and dual, you construct it from the log barrier problem, what you get is you will satisfy almost all the conditions of the KKT conditions, right? Except this complementarity condition, you are off by -1/t. Okay, you can check the the primal and dual we constructed and compare it with a KKT condition here. Okay. Yeah. Now I don't want to talk about too much about the implementation. Nowadays, very few people work on interior point algorithms, right? It's more important to get a high-level idea of the Barry algorithm, right? So what is a high-level idea of Barry algorithm is you approximate the indicator function with some sort of log barrier function, right? And the nice property of the log barrier function is it keeps the convexity of the problem, right? And also estimating the dual bound is really easy without even using a duality-based approach. You can estimate the gap being m/t. That's probably the two intuition you want to remember. The implementation is not so important, but you could take a look. The idea is you start from some small values of t, and then if your gap is less than or equal to epsilon being the threshold you set, then you can stop. Otherwise, you can increase this number t, right? As t increases, it will converge to the original problem, right? So therefore, there are actually two loops in the barrier method, right? The outer side of the loop is you are gradually increasing this number t, right? And the inner loop is this Newton step loop, right? You are solving a convex problem with equality constraints. Right? So they are in total two loops in implementing the barrier method. Okay, and then there are some high-level ideas of how do you choose t. I mean, if t is too small, of course, you need many outer iterations. When t is too big, maybe the first step will be difficult to solve, right? When t is big, the Newton solve will usually take more iterations. And then this mu parameter is how much you are going to increase t after each iteration. Right? If mu is too big, then the Newton method, the step will take more iterations. But when mu is too small, there will be more outer iterations. Right? So there is some sort of trade-off between the outer iteration and the inner iterations. But then people find out that in general, you don't need too much hyperparameter tuning for the log barrier algorithm. This is quite robust to those parameters. Okay. So now I will move to the primal dual interior point method. Any questions related to the barrier algorithm? Yes?
On the two slides,
Here?
before that, there was f star and f of x star. So, what is the difference between those two identifiers?
Yeah, sorry. So this, you mean this f star here?
Yeah.
So this f star denote the optimum of the optimal value of the original problem. Right, so you want to get an estimate compared with the optimal value of the original problem, but the g is a lower bound of f star, right? The Lagrangian is a lower bound of x star. If this Lagrangian function differs from x star by m/t, right? And then of course it is bounded compared with the optimal value by m/t.
The x star, is it a function of t or is just the right thing?
You mean this x star t?
Yeah.
Yeah, it is a function of t. X star t denotes the optimal solution of this barrier problem. Once you get a t, you got the optimal solution to this problem. So therefore, x star is a function of t. Right? As you gradually increase t, x star t will converge to the optimal solution. Okay. Yeah. Any other questions? Okay, now we will switch gears and talk about something called primal dual interior point algorithm. So here's an overview. But probably before I introduce this method, the overview doesn't make much sense. So I will just skip these slides, and then you can go back to the overview later on. Okay. So the idea of primal dual interior point method is similar to log barrier method. Right? So instead of using the log barrier function, right? Let's just apply some linear equation solver or nonlinear equation solver to this perturbed KKT conditions. Right? So now with these perturbed KKT conditions, right? The only difference with respect to the KKT conditions is this complementarity condition. Right? So you can think about as t goes to infinity, this system of equations will be exactly the KKT conditions. Now, since the KKT conditions are both necessary and sufficient, right? If we have an oracle that solves this system of linear equations while satisfying those inequality constraints, then we are done, right? We just find a feasible solution to the KKT system. But how do we solve this system of equations? How do we solve nonlinear equations in general using numerical methods? What? Newton's method, right? So we already talked about the second order Newton's method can also be derived from Newton's method for solving nonlinear equations, right? You just take the Jacobian as a first order approximation of the original problem, right? So if you have a system of linear equations, let's say g of x equals to 0, where g is a mapping from Rn to Rn, right? So what you can do is getting a first order approximation of this g of x using the Jacobian matrix, right? And then solve that first order approximation to get the solution to this nonlinear equation here, okay? And we can apply the same thing here, right? We are, I'm writing down all the equations together using this function R, right? So R is essentially a nonlinear function of the primal and dual variables, right? Using the perturbed KKT conditions. You don't need to be too concerned about this very nasty formula, right? This is nothing but the perturbed KKT condition in a vector form, right? So this is nothing but the equations in the KKT system, right? We are we are just removing the index and representing all the linear inequalities using h of x, and then let's say d of hx is nothing but the Jacobian of h of x. Okay. So now let's apply Newton's method for root finding, right? So the way you would do that is approximate the nonlinear equation, use a first order Taylor series expansion, right? The first order Taylor series expansion at y, then if you perturb it by delta y, is nothing but f of y plus the Jacobian times delta y, right? And similarly, you could apply this scheme to this system of nonlinear equations, right? Okay, so what would we get by solving this system of nonlinear equations? Maybe let's talk about version 2 first, right? So now the idea is let's apply Newton's method to the system of nonlinear equations, right? You take the Jacobian at this left-hand side, and then this is nothing but the perturbation you want to get, right? And the R on the right-hand side is sort of the residual of each of the equations. Right? So now if you apply this, you can get the root finding step such that the next solution you find is closer to the solution of the root for the KKT system. Right? You don't need to be scared by those system equations. You can just think about, I have same number of primal dual variables as a number of nonlinear equations, right? So that is a square system. You can apply a Newton's method to solve that system of nonlinear equations. Okay, so that's sort of the idea behind that. And there's another way to look at this problem is let's get rid of some of the variables by replacing the complementarity constraint. So recall that what we have is the complementarity constraint mu I times hi of x equals to minus 1 over t. Right? So whenever you have a ui, you have this complementarity constraint. Right? So you can use this equation to get rid of the ui, right? By replacing ui with minus 1 over t times h of x. Right? So now you get rid of all the ui's. What you are left with are the primal variables and the dual variables v. Right? You get rid of all the u's corresponding to the inequality constraint. That's just a very simple trick. So now you have a reduced system. Right? But then, of course, the equations becomes more complicated if you replace u by 1 over t times hi of x. Right? So similarly, you can apply Newton's root finding scheme to the remaining number of nonlinear equations. Okay. Okay. So then, before that, let's say ignore those equations. What is the conceptual idea of primal dual algorithm? Is you write down the perturbed KKT conditions, and then you have same number of nonlinear equations as a number of primal dual variable, right? Because we already know how to solve nonlinear equations, that's using Newton's method, then the idea is we will apply Newton's method to solve nonlinear equations to this system of nonlinear equations. That's sort of the high-level idea, right? Okay, without going to the details. Yeah, now, there is a similar concern. How do we get a duality gap, right? Even though we are solving this KKT system, it is a perturbed system, not exactly the original problem. For the barrier algorithm, we did some derivation and showed that the duality gap is bounded by m over t. Right? And then for this primal dual algorithm, we actually cannot get a good duality gap because the x cannot be guaranteed to be feasible, right? Since we are solving a perturbed KKT system without the barrier. So typically, people refer to this so-called surrogate duality gap. It is nothing but the sum of all the complementarity. Okay. Since we are solving a perturbed KKT system, right? The only difference is the perturbation over the complementarity constraint. Therefore, people use this as a surrogate duality gap. It will be a real duality gap if we have the primal and dual residual equals to 0. But usually, you cannot guarantee that. Okay. And there is a very long pseudocode for the primal dual interior point method. But I don't want to go to each step of the pseudocode, right? So don't look at the slides. Let's think about in high level what we need to do here, right? Again, the conceptual idea is we are applying a Newton solver to a system of nonlinear equations, right? But there are still some issues we haven't talked about because the KKT conditions not only contain those nonlinear equations, there are some inequality as well, right? Like the dual variable has to be greater than or equal to 0, and then we need to have primal feasibility, right? Those are also important issues there. Okay, and then we need to find some ways of, observing those feasibility constraints. Okay, then the other issue is usually when you design an algorithm, it always exists is you got a Newton step, right? Then how far you should go using this Newton step, right? You could think about there are similar ideas of line search and so forth, right? Now, the other issue similar to the barrier algorithm is you have this parameter t, which is a perturbed value, right? Maybe there are some schemes you should gradually increase this step t, right? As t is sort of, the larger the number t is, the closer you are to the optimal solution, right? Okay, so those are sort of the issues you want to consider when you are designing a pseudocode to solve this problem, right? Although the conceptual idea is there. And then you can find out some steps in the pseudocode to address these issues here. For example, what I told you is there are some inequality constraints you need to keep track of, right? You need to think about the step size such that you can maintain HL x to be feasible and all the dual variables being feasible, right? What will be the step size you can use? And then I don't want to go to the details here. The idea is you can use some sort of line search to make sure the point keeps feasible, right? And then you can read through these detailed steps on how they pick the hyperparameters such that you can guarantee you keep primal and dual feasible while you solve that nonlinear system of equations. Okay. Now, with that, let's talk a little bit about software, right? Okay, so like barrier algorithm can solve nonlinear programs, and of course it can also solve linear programs, right? The convex nonlinear program is a more general than linear program. You can also apply barrier algorithm or interior point algorithm to solve linear programs. And as a matter of fact, in commercial solvers like Cplex and Groovy, you can use barrier algorithm to solve LP, right? Now, one thing to remember is if you are only interested in solving a linear programs, right? You don't care about whether the solution you got is at an extreme point or not. You only want a solution, okay? Then barrier algorithm is usually faster than simplex, right? Because in barrier algorithm, there is no guarantee of extreme point or a basic feasible solution. So in some sense, you can think about simplex algorithm as I said, as a discrete optimization algorithm. Right? You are moving from one extreme point to another, and there are finite number of extreme points, right? But in barrier algorithm or interior point algorithm, the steps are gradient based, right? You don't know which point you will end up with. It is based on KKT conditions rather than based on things like basic feasible solutions. Yeah, and then in Groovy, there is also an option called crossover. Right. So in practice, you may see this in the solvers. So the idea of crossover is the following. Let's say you first use Groovy to solve an LP using a barrier algorithm, right? And then let's say you get a solution X star. Usually the X star is not an extreme point. Okay, so the issue with a point not being an extreme point is the solution may look very ugly in the sense that you have a lot of fractional numbers. Right? So Actually, I made a homework. You can try solving a same problem using barrier versus using simplex and see how the solution look like. Right? Because it is solving a perturbed KKT system, right? At termination, the t is not infinity, so you always have some sort of round-off errors in the barrier algorithm, right? So let's assume if you don't want this solution, right, and you really want an extreme point, then Groovy will do a step called crossover. So crossover means, push a barrier solution to an extreme point. Right, so this is what crossover means. First, you use a barrier algorithm to get a solution, but that solution is not an extreme point. Then crossover means it will try to push this solution to an extreme point, right? And sometimes what you will find out is when you use Groovy, crossover could take much longer than getting the solution from the barrier algorithm itself. Okay. But then if you're only interested in getting a solution, doesn't care about an extreme point. In some cases you do, right? Maybe you only care about the objective value. You don't really want a very good looking solution. Then you should use barrier algorithm and disable the crossover. Right? By default, Groovy will do crossover. Okay, that's some subtle things to remember. Okay, and then what about solving general convex problems, right? Groovy and simplex cannot solve general convex nonlinear problems. Then the commonly used interior point solvers are IP-opt, which was developed by Professor Larry Bigler's group at Carnegie Mellon. Actually, where I did my PhD. This is one of the solvers developed by chemical engineers. There are many solvers developed by chemical engineers. Still, I think IP-opt is still one of the best open source interior point solvers, right? And then there are also commercial interior point solvers like Mosaic or K-Nitro. Remember, Mosaic is a go-to solver for conic problems, right? It can also solve general nonlinear problems. Okay, then of course, if you are curious about their performance, you can go to the middleman benchmark and see where they are at, right? Okay, actually, you can go to the middleman benchmark whenever we talk about a new class of problem and check the solvers, how good they are for each type of problem we talk about, okay? Then, yeah, so here's the references I used, mainly the convex optimization book, and then this convex optimization notes by Ran Tipshirani. Okay, and in the next class, we will start talking about mixed integer programs.